Hello, welcome back. This is Calc 1 by Dr. Oz. This is the second video in a series of three. In the first video, we talked about how we can use the pattern recognition to find an indefinite integral. So today we're going to cover two learning objectives in one shot, which are about using the change of variables to find an indefinite integral, as well as the generalized power rule for integration to find an indefinite integral. All right, let's hit the road. All right, when we say change of variables for indefinite integrals, we are talking about rewriting the integral in terms of a different variable. Normally, we start with the integral variable to be x, but then after the change of variable, calling u to be a function g of x and looking at the differential of that, which is g prime of x dx, we rewrite the composite function form in the form of a very simple integral that you know hopefully how to integrate. So again, we're still trying to integrate a composite function, and we're looking at the pattern f of g of x, g prime of x. But if you can't see that pattern, the best way to handle that problem is to define a brand new variable called u. U is going to be the inner function, and then you look at the differential of that. Hopefully g prime of x dx is sitting outside next to f of g of x. So this way, this is du, and then this is f of u. So this integral is then rewritten in terms of the new variable u. And if you know an antiderivative of little f, in this case it's capital F, the integration results in f of u plus c. And as I said, after you are done with integration, you can go back to the original variable, which is x. So we can write this as like f of g of x plus c, because u is chosen to be g of x. So here you can just see u as like an auxiliary variable to simplify the integral, because this integral is obviously twice more complicated than this integral. And especially if you know an antiderivative of little f, the integration is just in one shot. Okay. All right, here's an example to practice the change of variables, or what we call like u substitution. We're trying to integrate radical 2x minus 1 dx. If this was just radical x to integrate, we wouldn't have any problem, because we would just write radical x as like x to the power of 1/2, and then we would just use the power rule for integration. But since we have just we have like 2x minus 1 inside the square root, we can't do integration in one shot. So for that reason, we call the inner function to be like u to be like 2x minus 1. Okay, and soon after you define u, you look at the differential of that. So you take the differential of u, that's equal to the derivative of 2x minus 1 times the derivative of 2x minus 1 times dx. Okay, that results in 2 times dx. Okay, so again, this is once you define the inner function u and you look at the differential of that, and in that case it's 2 times dx. And once you have this part, then using that, you have radical 2x minus 1 is equivalent to radical u, and you can solve this for dx. Since du equals twice dx, so 1 dx is going to be 1/2 du. Here we go. And now we're going to rewrite this integral in terms of the u variable. So in other words, I'm going to replace this radical 2x minus 1 by radical u. And dx as well is du over 2. Here we go. I have a simpler integral to work on. It's radical u times du over 2. And we know that constants are always pulled out of the integral. So I can simplify this as like 1/2 radical u times du. And I know how to integrate this, because all I'm going to do in the next step, you will see that I'm going to rewrite this as u to the power of 1/2. The integral is on u. So I'm going to use the power rule to have the antiderivative of radical u. And here we go. After we pulled out 1/2, we used the power rule for integration, and it turned out to be u to the 3/2 divided by 3/2 for the antiderivative of u to the 1/2. And we can simplify this further, just flip this number over, so it becomes 2/3, and you have 1/2 times 2/3 times u to the 3/2 plus c, and then 2's cancel, and then you get down to 1/3 of 1/3 times u to the 3/2 plus c. Don't forget to put the integration constant. And then the final step, you can go back to the original variable, which is in fact x, and putting the u equivalent version of that, which is 2x minus 1. And here we go. The integration takes you all the way to 1/3 2x minus 1 to the power of 3/2 plus c. Again, what I did here is just I plugged the u back in the final result after you're completely done with the integration. So this would be the value of this integral. All right. And this is a quick guidelines for making a change of variables. Well, first of all, you have to choose a substitution u equals g of x. This is the starting point. Sometimes if you're sort of like new in u substitution, you may choose the wrong u, but don't give up. Obviously, try to change the u variable so that the finalized integral is integrable by using the rules of integration. But at this moment, if you're again new in u substitution, you may choose the wrong u once the integral provided to you. That's okay. And it's best to choose the inner part of a composite function to be u. So here is just like rule of thumb. If you have a composite function, the inner part would be like a good candidate for the u substitution, u equals g of x. And soon after you have defined u equals g of x, then you look at the differential, which is g prime of x dx. And then after this moment, you have all the ingredients to convert the original integral to the u version of that. So in other words, we're going to rewrite the integral in terms of u, and we won't have any x-related term left in the neo integral anymore. Okay, so now I have a brand new integral written in terms of u, and you're going to integrate this by using the integration rules that we had the list given to you in the very first section of this chapter. So all the integration rules, including like power rule, trigonometric rules, and so on. And then once you're done with integration, you replace u by g of x, and eventually you're done at this step. And if you want to sort of like be in the safe side, since you integrated a function, the derivative of that function should be what you have inside the integral. So you got the antiderivative, take the derivative of that, so you should go back to what you start with. Okay, so what I'm trying to say is like you integrate this, and then you get f of x plus c. Obviously, once you take the derivative of that, you should get back to what you start with. That's exactly what I'm talking about. Okay, so the 6-step guidelines is super powerful, and I think it's way better than the pattern recognition if you're new enough, because pattern recognition is something that you must have like more experience with this type of integration of composite functions. But if you're new, start with defining u equals g of x, and you're going to gain that experience along the way about like who to call u. All right. So by using the skills that we just learned, if you have an integration of the form, a function raised to the power of n times the derivative of that, if you see this kind of form, the best function to call u is the inner function. So here u equals g of x, and du obviously is g prime of x dx. As you see, right next to g to the power of n, you have g prime of x dx, right? So here we go. This is your u, and this is your u to the n, right? U to the n times du is the integral when you rewrite in terms of u. And we know how to integrate u to the n by using the power rule, which is u to the n plus 1. This is u to the n plus 1 divided by n plus 1 plus c. There we go. And putting u, because u was originally g of x, and then putting u back, you get exactly this result. So this is called the generalized power rule. This is more like once you have a function raised to the power of n multiplying the derivative of the function you start with. So it's like, again, this is sort of like a pattern recognition. If you see this form, then you can always use the generalized power rule. Okay, and this is exactly what I just said. Once you have u to do, once you have u equals g of x, the new integral in terms of u is u to the n du, and if you integrate that, you have u to the n plus 1 plus u to the n plus 1 divided by n plus 1. Here we go, putting the u back, you get the integral to be g of x to the n plus 1 divided by n plus 1 plus the integration constant. All right. All right, I have like 5 super helpful examples to understand the u substitution. So the first one is the integral of 3 times 3x minus 1 to the power of 4. Who should we call u? Well, u is the inner function of the composite function, inner part of the composite function. That was the rule of thumb, right? So in this regard, why don't we call u to be 3x minus 1 so that du, hopefully, is coming along with dx. So 3 and dx terms here, hopefully that should pop here. And when you take the derivative of u here, it's like 3 times dx. Here we go. I have 3 times dx, right? I can rewrite them together. And then you have 3x minus 1 to the power of 4. Here we go. This is the 4th power of u. So now we rewrote this integral, right? I'll just clean this, right? So that now I have u to the 4th times du. And we know how to integrate u to the 4th times du. It's u to the 5th divided by 5 plus the integration constant. In fact, you can put the u back, and u was the inner part of the function. So this is the 5th power divided by 5 plus c. Okay, so this part A is of the form that you can use the generalized power rule for integration. Inner part raised to the power of some number, and you have the derivative of the inner part coming along with that. All right. And the next example is e to the x plus 1 multiplying e to the x plus x dx. So it's a complicated expression. So can we have like a function raised to a power of something, some number, multiplying its derivative? So here the natural choice is calling this function to be u, so that it becomes u to the power of 1. And the reason is that when you call u to the x plus xu, the differential of that is going to be e to the x plus 1 times dx. And here we go. I have e to the x plus 1 and dx coming along. By rearranging the terms here, so you have u to the power of 1 times du. So once you put this in this form, the rest is just a piece of cake, because you know how to integrate u du, and that is u squared over 2 plus c. And now I'm going to put the u back here, so that I'm going to get e to the x plus x quantity squared over 2 plus c. Okay. Again, you can accidentally call u to be this, but then du is not going to be anywhere in the integral. So that means you have 2 choices here if you want to use this u substitution. That's what I'm trying to say. If you call a wrong u, then you won't get anything at the end. So you have to restart and then call the other guy to be u. In the next example, I have 3x squared times radical x cubed minus 2 dx. This also goes perfectly along with our description here. The inner function, this looks to be my composite function, and the inner part of that is in fact x cubed minus 2. And the good news is that when you take the differential of that, that is 3x squared times dx. Here we go, I have 3x squared in dx, so by rewriting this expression here all the way, so you have u to the power of 1/2 times du. So you have u to the power of 1/2 times du, and we know how to integrate this. That is u to the 3/2 divided by 3/2 plus c, and putting the u back here, and you're done. Okay. So again, this is more obvious than part B, that the inner function in the square root is x cubed minus 2. That's exactly what I want to call u to be. All right, let's look at the next example. You have negative 4x divided by 1 minus 2x squared quantity squared. So this looks to be my composite function, and I'm going to call the inner part of that to be u, 1 minus 2x squared. When you do this kind of like u substitution, you make sure that when you take the derivative, in other words, when you look at the differential of this term, that better be somewhere in the integrand. And in this case, I have negative 4x times dx just popping over there. It's smiling at me, right? So this allows me to rewrite that expression in terms of u without having an x term left in the new integral. So this way, I have u to the power of minus 2 times du, and I know how to integrate this. I'm going to add 1 to the power and divide by the new power plus c, okay? And that is in fact negative 1 over u plus c if you simplify that. And putting the u back here, I'm done with this integration, okay? So this is a perfect example of generalized power rule for integration where you call the inner function to be u. And finally, we have an example involving trig functions. I have cosine squared x, quantity squared x, times sine x and dx. And here the composite function looks to be like cosine x quantity squared. Let me just rewrite that. Cosine x quantity squared. So I'm going to call u to be the inner part of that, which is cosine x. Okay? When you do this u substitution, du is going to be negative sine x dx, which is the derivative of cosine x, right? So now we have to sort of like look at this minus sign carefully. So I have sine x, I have dx here, right? This could be somehow what I got at the end, but it's the minus version of that. So I have to rewrite this as like sine x dx is negative du. So when I rewrite this integral in terms of u, I'm going to replace sine x dx by negative du, okay? So in other words, this is going to be u squared negative du, which is essentially same as pulling this minus sign out here, okay? So you can rewrite this as like minus u squared times du. Okay, once you integrate this, it's minus u cubed over 3 plus c, which is essentially equal to minus cosine cubed x plus minus cosine cubed x divided by 3 plus c, integration constant. All right, so we have gone through like 5 examples, and each of which are sort of like different from each other. So this, but this could be like a very good practice for you to use the u substitution to integrate composite functions. All right, this is the end of the video. This was the second video, and there's going to be the third video, which is going to be the next video. And in that video, let me just give you a heads up. I'm going to more focus on the change of variables to evaluate a definite integral, as well as evaluating a definite integral involving even or odd functions. All right, thanks for watching. I'll see you in the next video. Bye.